Austin. Thanks everyone for coming. I'm looking forward to a great afternoon, at least when the other talks start. I think it's going to be exciting. I hope you enjoy everything and the conversations later are great. So I'm supposed to do an overview here. There's no way to do all of that in 15 minutes. I could just read the names of all the contributors. That would take at least 15 minutes. But I tried to pick a few examples and give a little bit of history just to kind of frame up what the challenges have been and the progress we've been able to make building complete volume limited samples in the solar neighborhood. And I will focus on ultra cool dwarfs. The other speakers are mostly going to look at other things, which is great. We'll get a big picture here. I want to start with looking at why we'd want to study the solar neighborhood. As Ricky said, it's boring. We orbit a typical star in a mundane part of a very normal, boring spiral galaxy. But it's exactly that mundaneness that makes this important. We are in the normal. Studying our solar neighborhood gets us the picture of what much of the rest of the galaxy looks like. We're not studying the extremes, we're studying what most things are like. So characterizing that really well teaches us about astrophysics in many places. But we, of course, have to get it right. And when I'm talking about why volume limited samples, I like to look at the extreme opposite, a very severely magnitude limited sample, like naked eye stars. This is from Hipparcos. If this was the picture here, we would know nothing about M dwarfs, brown dwarfs, white dwarfs. We would have no Splinter today. Sorry. But a little more seriously, we'd be missing chunks of astrophysics, no degenerate objects, no fully convective stars. We would get the binary fraction wrong. We would think the sun is a faint star. We would just get things wrong. On the other hand, look at a volume limited sample. Here's a plot from recons. That's much more like it. Most of what's out there in the solar neighborhood, even 10 parsecs, is invisible to the naked eye. It's mostly M dwarfs. And the sun is, in fact, a brighter star. So volume limited samples tell us what is actually out there and helps us get the astrophysics right. Always be the gold standard for that. But it's challenging to do this. As anybody knows who's worked on this, it's hard work to put together a volume limited sample, first of all, and to get anywhere near completeness. Distances are hard to measure. Parallaxes take a time, and they're challenging. The search strategies that we use to find objects nearby always introduce biases into our samples and into our analysis. We have to correct for those. Crowded fields make things challenging. The binaries, yeah, if they're unresolved, they're contaminating our distributions, but we also want to study them and learn their distributions. So there are challenges. And because of that, I really want to emphasize that it's taken a long time to get to where we are now. I could cite many examples. I'll just look at a couple. One is Glise's catalog of nearby stars that has been through several editions. One of the landmark ones was published in 1991, out to 25 parsecs, almost 4,000 stars, was thought to be complete, but only down to the beginning of the M dwarfs. Beyond that, became less and less complete. No brown dwarfs at that point in time. But that took 34 years to get to that point. Painstaking work. And it has continued, of course. There's the 5th edition of this catalog, came out last year, now incorporating Gaia. Another big project that has contributed enormously, of course, has been Recons, published the 10 parsec sample I showed the plot from. They've been working, of course, to greater distances, and Todd will be talking about that in a little while. Also complete, but not all the way down, just midway through the M dwarfs, approximately at 10 parsecs. Challenging to get all of the objects. And I'm saying twiddle 20 years here. That project is ongoing. So it just takes time to do this, unless, of course, you get a major advance in telescope technology. And then Gaia comes along and gets a billion parallaxes, and suddenly you have a 100 parsec sample, and at more than 50 parsecs, it's complete down through the end of the M dwarfs. And it does that in a few years. Thanks, Gaia. But Gaia itself has limitations too. It's optical. It doesn't see a lot of the brown dwarfs. As Celine talked about earlier, it's still, it can be challenged by confusion. It doesn't get all the binaries right. We still have work to do looking for missing things and characterizing what's in the sample. So I'm going to focus now on ultra cool dwarfs for the rest of the talk. Again, others are going to look at other parts of the sample. So Classic slide of ultra-cool dwarfs, the late M dwarfs and LT and Y, which includes all the brown dwarfs, which cool down as they age, making them unique in that way compared to stars. And pointed out that volume-limited samples are challenging to assemble. Well, all of those challenges are present for ultra-cool dwarfs, along with the fact that they are quite faint and in the infrared, so we need different detectors. And you need pretty much multi-wavelength data because the way we found them is in large sky surveys like 2MASS and WISE and Pan-STARRS. Need the multi-wavelength data, and you're sifting needles out of the big haystack. So a lot of work there, a lot of challenge to make sure you're characterizing your selection, that sort of thing. And we didn't start finding ultra-cool dwarfs until around 30 years ago. This from the ultra-cool sheet shows discovery years. It's not everything, but it's fairly close to everything. It shows that, there was kind of a, in the couple decades ago, there was the big ramp up of discovering objects. Maybe it's tapered off a little at this point, but a lot of work that took decades to do to get us to where we are today. I want to look now at a couple of goals, results for volume-limited studies of ultra-cool dwarfs in our solar neighborhood. One of the big ones, of course, has been the mass distribution. This is often characterized as a power law with a index alpha that characterizes it. What you need to know here today is if it's 0, then that means it's a flat mass distribution. If it's positive, that means you have more lower mass objects. And just characterizing the results very quickly from the last few decades, for higher mass stars, we've got a consistent measurement in many environments, a clear value for alpha. For low mass stars, and we don't know. There's been some conflicting results. We're making progress now, but that's the basic situation and the motivation. And along with mass distribution, we'd also like to know the age distribution of these objects, often parameterized as an exponential, and that beta is the key parameter. If beta is 0, flat age distribution. If beta is positive, your population leans toward the old. These are difficult things to figure out for ultra-cool dwarfs. Hey, they're difficult for stars too, but there is no brown dwarf main sequence. Instead, there's a mass, age, luminosity degeneracy. So you can't look at a brown dwarf and tell much about it besides its luminosity and temperature. So we build synthetic populations based on assumptions for alpha and beta, compare those to what we observe in our samples, and try to back out constraints on the mass distribution and the age distribution. People have been doing this for a couple of decades now. If you want to know more about all the methodology behind this, I suggest reading Bergasser et al. 2004, Allen et al. 2005. We've been trying to do this for 20 years. In star-forming regions where you have a single age population, the results for alpha have tended to be a little bit on the positive side and fairly consistent with each other. You could do a whole talk on that as well, but a quick summary. But looking in the solar neighborhood, there have been actually quite a spread of results, mostly in a different range. These were, people doing the best they could with the samples they had at the time, which tended to be more limited in range and not complete, not volume complete. And so you could see the scatter. The challenge in this was getting enough leverage to do population synthesis with samples that were smaller and less complete. And that's just the mass distribution. For the age distribution, there was really very little just because the samples didn't offer much leverage. The most common thing was to assume that the age distribution was uniform because there wasn't much way to get around that. Well, things have finally changed now because we have a couple of volume-limited samples in ultra-cool dwarfs that are complete, or at least approaching completeness, and the corrections are small. And these cover L's, T, and Y dwarfs. So more than 500 members means we actually get some statistical heft now. Really can actually begin to get constraints on things. And I want to point out as well that David Kirkpatrick et al., their new sample includes not just the LT and Y dwarfs, but also the stars and white dwarfs that are in this volume-limited sample. So they've begun to work on the mass distribution for the entire sample, which is just awesome. That's been a goal for a long, long time. Well done. I think this is a good time, again, to point out that We didn't create these samples ourselves. I know I certainly didn't. My work is built on the shoulders of many, many other people's work. So I want to acknowledge there's a ton out there. I'm sorry if your name's not on the slide, just a ton of work. I filled in some gaps and finished things off, but I was lucky to be there at the right time. Okay. What I can say is that now we're able to get some real constraints on the mass and age distributions. I want to thank my teammates for this particular project. This is our paper that came out this year. What did we find? We found an alpha of close to 0.6. That's what Kirkpatrick et al. Have also found. So there's still some work to do, some differences in method, but we seem to be converging on the same thing. We finally have the samples that allow us to do this. This is great. And for age distribution, my group has found that it actually leans strongly toward the young. Beta is negative. That assumption of a uniform age distribution isn't correct. More work to be done there, and I'm really interested in what the full sample of stars and brown dwarfs will tell us about that. So these are things that we're finally able to do because we have complete volume limited samples. Another one like that, there we go. Celine showed in her talk earlier this morning this color magnitude diagram showing a gap in the middle of the LT transition right there. Whoops, didn't mean to tap that. Okay, this is color coded by the source of the parallaxes. But that gap is a clue about evolutionary pathways, another major goal of volume limited samples. It suggests there's a short-lived phase in this color space, something for modelers to chew on. I want to highlight that if you just make this plot with everything that had a parallax, at least at that time, this is what it looks like. You don't see a gap. But with a volume limited sample, the gap pops out. This is the key sort of thing. And historically, I will also say, we have thought that gap might be in other places. I published that at one point, but now the volume complete sample actually shows us where it is. Okay. I'm going to jump ahead slightly and start looking to the future. So what's coming up shortly? Well, we know volume limited samples are going to get larger. We have Euclid's online, LSST is going to come online. But let's not forget that we still haven't found everything in the solar neighborhood. This has been pointed out a couple times today already. Here's the 10 parsec sample a couple of years ago. Here's what's been discovered since 2010. And I don't think I have all the Y dwarfs on there. So do you think we're done? I do not. There's still more nearby to find out. Okay. What else about galactic structure that really matters here? Our samples contain thin disk, thick disk, halo members. Kinematically, Jackie Faraday, Sarah Schmidt told us this 15 years ago. Sebastian Lepine's been working on it with M dwarfs for longer than that. We have these different components that impacts ages, metallicities, a lot of different things. We need to be incorporating that in our analysis. Jen Winter showed us how to do that this morning, looking at the kinematics of the M dwarf binaries. Larger samples are going to take us outside of the galactic plane where these different components of the galaxy are more and more important. So that assumption of uniform spatial distribution, which you can find in my papers, that's not going to work anymore. We're going to have to account for structure. Okay, dynamics. Galactic dynamics matter too. Things are moving around in the galaxy. I showed before the young leaning distribution that we found, which has been found previously as well by Dupuy and Liu for looking at the masses from dynamical masses from binaries. That actually has a natural explanation. Dynamical heating. As objects orbit around in the galaxy, interactions tend to stir them up out of the galactic midplane. You could see that in the video that Celine showed at the end of her talk this morning. So young leaning distribution is a natural consequence of the dynamics in the galaxy. Oh, there's more than that. Another thing you could see in Celine's video is that take any volume limited sample you want around the sun, and it quickly disperses. We would expect, just based on the tangential velocities of nearby stars, that none of them will be nearby in a few million years from now, never mind 4.5 billion. So our volume limited sample is not static. Stars go in, stars come out. Want to quote a paper from Zubiar 24, just came out, looking at the kinematics of white dwarfs in the solar neighborhood. Their conclusion is that it's transitory. So what actually is in our sample? What does it represent? It's not the stars that were born nearby. What is it representing? According to Zubiar et al., stars may be coming in from as much as 2 kiloparsecs away, and that's just the thin disk component. So we need to consider what this means in our analysis, something we've maybe gotten away without doing before, but we've got to look at it, especially as our samples expand. So I'm going to put up my summary here, say thank you, and take questions.
Okay, for questions, I'd like to ask people to give your name, affiliation, and then your question.
Fred Adams, Michigan. You showed that the IMF goes like alpha minus 0.5-ish or 0.6-ish. And then earlier today, I think we had learned that there's 4.4 times as many stars as brown dwarfs. Can you comment on the consistency of those? It depends on where that range is and so on. So make those two things. Make those two things work together.
Yeah, I think those numbers are both in your paper. One thing I would say is, if you're just counting stars and brown dwarfs, something that we haven't identified yet is the lowest mass object you could make, the low mass cutoff. The positive alpha tells us that there are more and more stars as you get to lower masses, more and more brown dwarfs toward lower masses. There might be a sharp cutoff, there might be a taper, we don't know, but we're not sure what the total is there. So maybe there's a lot, and that would explain that fairly high, or I guess fairly low stars to brown dwarf ratio. Is that answering your question?
No, it goes the other way around. There's 4 times as many stars as brown dwarfs.
Yeah. There's a much larger mass range for the stars
Yes.
to occupy.
By a lot.
Yep.
Other questions? Chris?
Chris Tinney, University of New South Wales. Since this is the Splinter section, and you asked the question, I'll try to. I would like to make a comment that so Celine's wonderful animation actually told us today that our little neighborhood disperses, but that also means at the same rate things are moving out, things are moving back in. So we're doing some sort of sampling of some large part of the galaxy. If you want to wait 5 million years, you get a different solar sample, and you might get a different answer. I'll be surprised if the mass function changes, but I would not be at all surprised if the spikes we saw in that birth rate as a function of time does not change when you do that. So
one thing that we may be able to do when we have larger samples, LSST and other telescopes take us further away, is build a volume limited sample that's 50 parsecs wide, but over there, and see what that looks like. We don't have to wait 5 million years for them to come. That'd be an interesting comparison.
Up here?
Hi, Zach Way from Georgia State, and I have kind of a philosophical question. So one thing that I think you miss out with volume limited samples are outliers. Right? So you had any ideas of quantifying what we could be missing by just looking at a certain distance?
Yeah.
As halo stars.
Yeah, we probably have a few in our samples, but not enough to say a lot statistically. Expanding beyond ultra cool dwarfs, we don't have any B stars or nebulae for that matter in our sample. So of course we're missing things. Larger volume limited samples may get us into more rare objects. As a brown dwarfer, I'm particularly interested in the very young red objects. We've got a few in my 25 parsec sample, but a few out of 500 has fairly large errors on it. Get a bigger sample and you might know a lot more. So yeah, that's absolutely a good thing to look at.
Okay, and we got time for one more question.
Hi, Kim Ward-Duong, Smith College. Thanks for a wonderful review. I was wondering, I was really intrigued by this idea that the solar population is sort of skewing younger in our solar neighborhood. And I was curious if you think there's any room in boundary space for like a cold nationwide dwarf population that might like tip that balance to older systems.
Hi, Kim. Yeah, there's room for that.
You can repeat the question.
Thank you. Okay, so Kim asked, I talked about the young leaning local population. Kim asked if there is space in there for like a cold, older white dwarf population. And I think the answer to that is definitely, because I know we haven't found all the white dwarfs. Ages for white dwarfs somewhat challenging, although we saw a talk yesterday finding deuterium in one that helps us, with a constraint there. So yeah, that is one of the frontiers in our volume limited sample still, that will tell us something about ages. At the very cold end, it may actually give us more information on the mass function. That could change a little bit as well. But yeah, any conclusions we draw now are, well, still pending data coming in. So.
Okay, let's thank our speaker again. Okay, next up, we have Catherine Clark. My consultant. And she's going to be telling us about nearby M dwarfs and the role of stellar multiplicity.
Oh, yeah. Okay. Okay, hello everyone. For those of you who don't know me, my name is Catherine Clark. I am a